I'm Brian. You can call me that. I recently graduated from Carnegie Mellon, and I'm now working with in the Department of Computer Science at National University of Singapore. So my former advisors at Carnegie Mellon are John Dolan and Pradeep Khosla. So the talk today is about using entropy-based approach to perform adaptive path planning for environmental sensing. Now, typically, the robot exploration problem requires sampling of the entire terrain to learn about it. But suppose that we only have very limited sensing range. Say in a robot, you only have a point-based sensing. The complete coverage is not practical in a very large region with a few small hotspots. I will show you what I mean by hotspots later on. So this kind of scenario happens in application domains such as planetary exploration, like mineral prospecting, and in ecological sensing, like monitoring of ocean phenomena, plankton blooms, and say forest ecosystems. Now, in this kind of environments, static sensor placements are actually discouraged, because if the static sensors are placed in locations which are not in hotspots, they cannot reposition themselves to locate a hotspot. So in this case, a mobile robot team is actually more advantageous because it can perform high-resolution hotspot sampling. Let me show you what I mean by hotspots. So on this diagram, you can see a map of Chesapeake Bay, which is in Maryland area. So I call this a hotspot field. So what are the characteristics of this hotspot field? You can see that at any location within the map, you have some continuous measurements as shown in the scale. And secondly, if you put together all the measurements of the map into a 1D frequency distribution, you notice that you have a positively skewed distribution, which is shown here on the right-hand side, where you have a lot of very low measurements and very few high measurements. Now, the third thing that you can observe in this field is that the measurements are spatially correlated. What that means is that between any two neighboring locations, the measurements are very close to each other. So if you look at the map, you can see that on the left-hand side, you will see like 2 to 3 hotspots. So in these hotspots, you notice that they exhibit extreme and highly varying measurements as compared to the rest of the field, which is like on the right-hand side, which is more gently, it has a gentle slope. So now, with respect to this map, I want to investigate this question. How does a robot team plan observation paths to minimize the uncertainty of mapping this hotspot field? So there are 3 important issues in this question. First is the path planning. The second thing is the mapping uncertainty, which we want to capture using a spatial model. And the third thing is, of course, the hotspot field. Just now I've mentioned the properties of the hotspot field that I have. So the planning and the modeling techniques should be able to fully exploit the environmental structure that I've mentioned just now. So these are the 2 characteristics of the hotspot field. So spatial model. In my research, I'm looking at this class of probabilistic models, such as the Gaussian process and the log Gaussian process. So the good thing about these models is that they can capture continuous measurements and they can capture spatially correlated. Later, I'll show you how the log Gaussian process can be used to capture things like the positively skewed measurements. The other good thing about these models is that it's very easy to come up with formal measures of mapping uncertainty. For example, you can use the mean squared error criterion or the entropy criterion. So how do we do planning on this model to minimize the mapping uncertainty? So on the path planning side, we want to come up with algorithms that allow us to minimize the mapping uncertainty. So some of the desirable properties are things like whether we want discrete or continuous states. and whether we want Markovian or non-Markovian exploration strategies. So in my work, I'm looking at continuous states because this allows the policy, the exploration policy that I have to capture the continuous measurements of the hotspot field. And I'm using non-Markovian assumption because with this, the policy can be informed by the entire history of spatially correlated measurements. Now, there are two other important properties, like whether it's greedy or non-myopic, and whether it's adaptive or non-adaptive. So I will explain these two properties later on, but bear in mind that these properties help the exploration strategies to exploit hotspots or clustering phenomena as compared to greedy or non-adaptive techniques. So previously, in a previous work in AMAS 2008, I've come up with a framework, a problem framework called the Multi-Robot Adaptive Sampling Problem, or MASP. So this problem framework captures all the properties that are mentioned on the left-hand side. And in particular, for this problem framework, I'm looking at the mean squared error criterion. So in the current work for this ICAPS, instead of looking at the mean squared error criterion, I'm looking at the entropy-based criterion, or the same framework. And what is different about this new framework is that later I will show you that the solution is actually independent, or the time complexity is actually independent of the map resolution that I have, which is a huge gain when it comes to calculating the solution. So let me talk a bit more about the planning part of my work before I go on to the modeling and how I do planning on the modeling, on the model. So I will talk about the information-theoretic MASP, which I call IMASP. It's a sequential decision theoretic planning under uncertainty framework. So since it's sequential, it becomes a multi-stage exploration process. The cost function that I'm looking at is the posterior map entropy. So I define the posterior map entropy as the joint entropy of the measurements that are at unobserved locations given the observed data of the robot paths. So initially, before the robot starts to move out, it doesn't have any data, right? So what happens is that you have to select paths that minimize the expected posterior map entropy because the data is actually unobserved. And that's what I mean when I want to come up with a policy to collect the optimal data, which is to select paths that minimize the expected posterior map entropy. And two desirable properties that are in this framework is that, firstly, the exploration policy is non-myopic. What this means is that the choice of the current observation depends on the expected payoff of the future observations. And the other property is the adaptive property. So in my work, I have formalized the notion of adaptivity, what it means to be adaptive. So what that means is that the choice of the current observation, it depends on the past observations. So let me talk about a bit more on what I mean by adaptive. How do you tell if a strategy is more or less adaptive than another strategy? So suppose that we have an exploration mission where the robot has to explore 10 locations. Now, if you recall that for an adaptive policy is to select new locations at each stage, which depends on past observations. So very simply, we can first look at one of the extreme case, which is the non-adaptive policy. So in the non-adaptive policy, it does not depend on past observations. It selects all the locations to visit, which is denoted by this X1 at the bottom. And this is done in one stage. Now, on the other hand, if I want a strictly adaptive policy, when I select every new location, it's going to depend on all the past observations that I have in order to make my decision. Now, we can enumerate a spectrum of adaptivity for all the various exploration policies by expanding the number of locations that you can select at each stage, as you can see here. So now that I've told you about adaptivity, the cost minimizing IMSP is actually a set of dynamic programming equations whereby if you have a certain degree of adaptivity and you fit it into the dynamic programming equation, it will produce, firstly, the optimal adaptive policy as well as its expected performance. So in this case, when I have different degrees of adaptivity, I'm able to generate different expected performances of different policies of different adaptivity. And this allows me to cover the entire adaptivity spectrum. And with this, I'm able to, in this work, I'm able to subsume various existing non-adaptive model-based strategies. One of the previous results of my work is that the expected policy performance, it improves monotonically with higher degrees of adaptivity. And it's actually not more costly to derive an optimal adaptive policy than a non-adaptive one. So now, just now I've explained the cost minimizing IMSP. I want to transform it into a reward maximizing problem. Why do I do that? There are a few reasons. One is because of the time complexity. Secondly, it's because it allows me to see the various observation selection properties. And thirdly is because I'm able to show that the reward maximizing problem is actually convex in nature. And this allows me to use various inequality tools to solve the problem. So the original cost minimizing objective is to minimize the expected posterior joint entropy of the measurements at the unobserved locations. The time complexity of evaluating that cost function, it depends on the map resolution. Now, when I transform it into a reward maximizing objective, what happens is that in this problem, I try to maximize the expected entropy of the observation paths. And in this case, since I'm only looking at the entropy of the paths, the time complexity of solving the problem approximately is actually independent of the map resolution. I've shown that analytically in the paper. And for those of you who knows what is maximum entropy sampling, what I've came up with is a novel adaptive variant of the maximum entropy sampling. The other thing that I've shown in my paper is that the original cost minimizing objective is actually equivalent to the dual reward maximizing one. So what this means is that the two policies are, they coincide, they are the same. And intuitively, how do you show that is to make use of the chain rule of entropy repeatedly in the proof of induction to show this. Now, on the other hand, just now I mentioned in my previous work that I've made use of the MSE, or mean squared error criterion. The dual of that problem, there's no such computational advantage in the sense that it's not independent of the map resolution. Because the dual problem is actually maximizing the sum of expected mean squared error reductions, which involves all the locations in the map. Now I'll move on to talk a bit on the modeling technique before I tell you how to apply the planning on the model. Now, I've used the non-parametric probabilistic models like the Gaussian and the log Gaussian process. So for those of you who know what is geostatistics, they are often known as kriging. Now, perhaps a lot of you are very familiar with this thing called Gaussian process. So we can actually generate a sample from a multivariate Gaussian distribution, and you'll get this. Now, to get a log Gaussian process, all you need to do is to take the exponential of all the measurements, and it will result in that map there. Now, if you can see from these two diagrams, the hotspot for the log Gaussian process is actually more pronounced than the hotspot for the Gaussian process. On the other hand, the areas which are of lower measurements, over here, or should I say over at the log Gaussian process, is more gentle than the ones in the Gaussian process. So this can also be observed when you put all the measurements together into a 1D frequency distribution, whereby you see in the log Gaussian process that you have a greater range of high measurements and a smaller range of low measurements. Now, if you take the log of all these measurements, you will get something like this one here. Right? It expands the range of the low measurements and it decreases the range of the high measurements. So if you look at the 1D frequency distribution, it coincides with the hotspot field that I've shown to you on the Chesapeake Bay beforehand. And you can see that the frequency distribution coincides. And if you look at the maps itself, the hotspots are also very similar in nature, in the sense that they are more pronounced. So of course, we can directly try to apply this Gaussian process to model the hotspot field, but that's not desirable. When you try to model the hotspot field using the Gaussian process directly, what happens is that there's this aspect of it called the stationary covariance structure. It's going to be violated by the skewness of the measurements as well as the extreme measurements. And in the reference I provided, it caused problems like prediction of very large hotspots, which may not be the case, and very small variances at locations of hotspots. So we don't want that. So one remedy that the geostatistics people have came up with is to take the log of the original measurements and use the Gaussian process to model the log measurements instead. Now I'll show you what's the difference between the two. Now we want to apply the planning technique on the model. So just now I mentioned about the Gaussian process. In short, what that means is that the joint distribution over any finite subset of the measurements is Gaussian in nature. One important property of this Gaussian process is that the posterior variance is independent of the measurements. And this so just now I mentioned that we are taking the log measurements. So the entropy criterion is optimized in the transform log scale. And using the property that I mentioned before, I'm able to show that the optimal policy is independent of the measurements, which means that it's non-adaptive. So what this means is that the adaptive IMSP can be transformed to a non-adaptive one, and the multi-stage planning process can be reduced to a single-stage deterministic planning problem. Now, if you look at the policy later on, it will exhibit only wide area coverage property. What this means is that it sends the robots out into sparsely sampled areas. Now, using the observations that are selected from the wide area coverage by the Gaussian process, it may not map the hotspot field well, because the hotspots with highly varying measurements are actually undersampled. And those are areas where you see a lot of highly varying measurements. So in this case, if we use the log Gaussian process to model it, what happens is that the entropy criterion is optimized in the original scale rather than the log scale. And what log Gaussian process simply means, just now I've mentioned, you just take the log of the original measurements and it will give you the Gaussian process sample. So if we apply the planning to a log Gaussian process model, I'm able to show that the optimal policy depends on past observations, which means that it's adaptive in nature. And the second thing is that the policy exhibits wide area coverage as well as hotspot sampling properties, meaning it's able to send it to sparsely sampled areas as well as to areas where there are hotspots. So to solve the IMSP problem, the first computational difficulty is with the continuous measurements. To resolve that, we are able to show that the reward maximizing dual is convex in the measurements. And this allows me to use the bounding, the inequality tools to bound the solution. And these bounds are actually piecewise linear functions to approximate the value function from below and above. And as a result, I'm able to come up with a result that the approximately optimal policy is E-optimal for achieving the entropy criterion. What that means is that the policy is not worse than the optimal policy by epsilon. So the other thing is that I can make use of these bounds to bound the performance advantage of adaptivity. The second computational difficulty I will not mention here, but it has to deal with the non-Markovian structure, and I make use of real-time dynamic programming technique. So let me go on to the experimental results. So on the original map, which is in gray now, grayscale, it is an exploration region that's discretized into 148 sampling locations. There are 2 robots starting at the axis. Now, there are 20 locations that are randomly selected as the known data for me to determine the hyperparameters of the model. So there are 2 metrics that I looked at. First is on the posterior map entropy, which is the measurements at the unobserved locations, given the data that's collected by the robots. The second one is on the mean squared relative error. So the second metric allows me to use the ground truth measurements for evaluation. So for both of them, the lower the metric, the better. So the summary of the results, the IMSP policy achieves the lowest entropy and the lowest error as compared to entropy-based techniques such as the non-adaptive and the greedy ones, as well as it is lowest as compared to the mutual information-based strategy in that reference. Secondly, it can achieve mapping performance comparable to the MESP policy, which is the one with the mean squared error criterion, using significantly less time. It takes like 2 minutes as compared to 3 hours for the case of 2 robots. Thirdly, the incurred planning time is less sensitive to a larger robot team size, where it increases by 1.73 times from 1 to 2 robots as compared to 3.65 times. So for the last slide, if you see the paths, which are black, these are the ones that are produced by the IMSP. It sends the robots through the hotspots themselves, whereas the ones in gray are the ones that are non-adaptive in nature. It sends it to areas which are sparsely sampled. And this produces those error graphs on the left-hand side. The top one is for the adaptive, and the bottom one is for the non-adaptive, and it shows a higher degree of error. That's it. Right.
Only there.
Right.
Okay. And what's the dynamics of the environment in general, and the kind of hotspots that you are considering? Are they statics, or do you look grounded?
Oh, so in this current work, I assume that the hotspots are static in nature. But in order to capture hotspots that are dynamic, all we need to do is to add a third variable as input, which is the time variable, and it will allow you to capture the hotspot. Yep. Oh, sorry.
Actually, I have a similar question. I mean, it's not clear to me if the map are given to you and then you are producing the most efficient trajectory for your robot, or are you actually producing the trajectory as you are sensing the environment? So,
yeah, I'm actually producing, I have a policy that takes into account the measurements, and this policy directs the robot. It doesn't use the map as information. But of course, if you want to talk about the locations wise, of course, we assume that the robot knows its location, but not the measurements. Yeah. Could you speak louder?
If I understand this diagram correctly, this is the Plankton density field, but you're actually trying to minimize the uncertainty in your estimation of the Plankton density field, right?
Right.
How do you go from one to the other? Do you have an ensemble model or something that's predicting the uncertainty as well, or? So, just now I've mentioned, to reduce the uncertainty,
there is a equivalent problem, which is to maximize the entropy of the paths. So if the robot tries to capture the maximum entropy of its own path, it's able to reduce the uncertainty of the map optimally. Yeah.
So why does it consider there are obvious, the oceanographers would typically fly transects through that or fly along the edge of the blue. Why does your planner not consider those alternatives?
You mean on the outside?
Yeah, I mean that's actually the typical standard routine that the oceanographers would use is to fly zigzag along the edge of the blue.
Right. So usually what happens is that if you are just interested in wide area coverage, which is to send the robots to sparsely sampled areas, that is exactly what the plan is. By sending them, say in a straight line.
Normally they would fly along the edge of the blue because that's the highest radius of the plane.
I see what you mean. But that's
Along the edge.
right. That's a different problem. So in that sense, you are trying to maximize the amount of information on the temperature gradients or the field gradients that you have, whereas this one, I'm trying to minimize the uncertainty of the field. So that's another interesting thing that you can look at. Yeah, but it's a different criterion. Yeah.
So you mentioned that you assume that your environment is non-macro because then you can plan based on your history of observations, right?
Right.
But what if you assume it's macro and then you use some kind of lead state and use this to plan? Would that be more efficient?
Yep. So in the last part of my thesis, I've looked at using the Markov assumption in this work. And what happens is that, of course, there's a huge computational speed up, and I can come up with theoretical guarantees with respect to how the spatial correlation in the field relates to the Markovian properties of the policy itself. Yeah, but it's not published yet.
Okay. Well, thanks again.
Thank you.